Okay. I hope it's working. I hope it's recording. We'll see. Okay. Yeah, let me just wrap up again on golden section search. And the idea is we've got, let me just expand this a little bit. Okay, and so I'm going to call this the lower bound. This will be the upper bound. And then this is x1, and this is x2. And the idea is that, you know, from the lower bound to x1, this represents about 0.618 of the way. And from the upper bound down to x2, this is also about 0.618 of the way over, okay? From the, I guess I'll say 0.618 times the difference from upper minus lower. Okay. And then, you know, we've got some kind of function that we want to optimize here, right? So, and the idea is you evaluate this at these spots right here and here, okay? And you know, kind of we start off. We know there is one local min between lower and upper, okay? And we evaluate the function at x1 and x2. Okay, so we get f of x1, and we have f of x2, and we find f of x2 is less than f of x1, okay? And because of this, now we know the local min cannot be between x1 and upper, because we know a smaller value exists between x1 and lower, namely x2. Okay, and so because of that, we can eliminate one side of this thing. So we can, I guess we can just kind of cross this side out. So we can eliminate this. And the nice thing about using the golden ratio to decide where x1 and x2 is, okay, because we used the golden ratio to determine where x1 and x2 are, okay, we can reuse the value x2 and f of x2, okay? So we have to, so here is kind of the ratio here. So if I shrink this down, to right there. Let's see if that works out. Something like that, okay? Then this is x2, and then now I will get a new okay. So I guess for iteration 2, this will be the lower bound, and then this will become the new upper bound, and this will become x1, and this will become x2, okay? And so this distance from here to here is going to be around 0.618 times upper minus lower at the second iteration. Okay, and then similarly we'll have this right here. Okay. All right, and then so I don't need to recalculate this. I already have this, and I just need to calculate this. Okay, so I calculate f of the new x2 okay, and this value is less than f of the kind of the original f of this value. Okay, so I don't know how to appropriately label these things. Okay, so you find this is so then we can eliminate this side. Okay, so now we can eliminate from lower to x2. Okay. And then we would just continue repeating this process until we get, so now we know that the minimum has to be between here and here, and then we would find another location, you know, dot, 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 and then continue on going there and there, okay? And so that's kind of how golden section search goes. It's iterative in that you keep partitioning off sections using the golden ratio. To kind of find a small area where the minimum is going to lie. And then once the difference between your lower and upper bound is small enough, you can just say the minimum is somewhere in the middle there. Okay, so once the difference between the lower and the upper bound is less than some value, say 10 to the minus 6, you can just say, okay, the minimum is, you know, this arbitrary value. Okay, and we've coded that up for you. It's already provided as part of your homework using, you know, the golden ratio and all of these things, and you can you know, work through this. Okay, and you'll notice that the calls to f itself is you know, has been minimized. Okay, which is good. Okay, all right. I want to talk about coordinate descent. Okay, and this appears in your homework, and this allows us to do kind of multivariate optimization. Okay, so univariate optimization, I guess depending on how expensive it is to evaluate a function, univariate optimization is often not super interesting. Okay, so I'll say is relatively easy. Okay, it's you can just technically you could just evaluate the function like at every single value, and then you just pick the smallest value, right? So you could just say, let's evaluate the function from, say, like 0 to 100, and then and you can just iteratively evaluate that, and it's not very costly. Okay. However, if you start having multivariate functions, this kind of grid search is no longer feasible. Okay. So in your homework, you have to graph these things, which in a sense defeats the purpose of these algorithms of searching for a minimum. Okay. The algorithms that we have for searching for minimum is like you start at some point, you evaluate the function, you get the derivative, or you get the secant line, and then you get another location, and you go iteratively from there. But at the beginning, I think I start off with like x is some sequence from like -3 to +3 or something, and you end up, the computer has to evaluate like 1,000 locations, and it uses that to help plot the line, right? And then you can just visually inspect where the minimum is, right? So univariate optimization is relatively easy, even without an algorithm. We can perform what's called a grid search, which is just evaluate the function at a whole bunch of locations. Okay. So grid search at many locations, and then pick the smallest value. Okay, so that would be something like x is going to be sequence from, say, -3 to 3 by equals 0.001. Okay, and then you just f of x, and then you just basically say which dot min of f of x. And then I guess you could subset your x based on that. And this will give you kind of the, and this is the x value that produced the smallest fx value. Okay. So this is relatively computationally expensive because you have to evaluate the function at every single one of these locations. So this is probably like around 6,000 locations, 6,001 locations, and you have to evaluate the function at all these things. But if the function is simple, it's not that big of a deal. Okay. I guess an exercise you can think of is pretend that every time you call the function on a value, it costs you $1 or something, right? So this grid search would cost us $6,000 to perform, okay? Because we would, I've got basically 6,000 values of x here, and I've called f. I've had f evaluate 6,000 different values of x, and I can pick the smallest one, and it's going to be this thing. Okay, so grid search is not optimal, but it's simple and it works, right? And this is basically what we use to produce a plot, because effectively, we call basically plot x and fx, and it creates it joins all these dots together into a smooth line. Okay, grid search becomes really bad when you have more than one dimension, okay? Okay, so you might have, we have some function of two variables. Okay, so we have f of xy. Okay, and so we might say x is sequence from -3 to 3 by equals 0.001, and then I could have y is sequence from -3 to 3 by equals 0.001. Okay, so this has a length equal to basically 6001, and this also has a length of 6001. Okay, and so if I did a grid search on x and y, how many times do I have to evaluate f? So grid search would evaluate f for every pairing between x and y. Okay. So this would be, 6001 squared on the order of 36 million, right? So if you thought it cost a lot of money, $6,000 to do this grid search would cost us $36 million, okay? We would have to evaluate all of these things, okay? Okay. And that's effectively, when we plot the contour, we're effectively asking the computer to do this. Okay, we're effectively asking the computer to calculate all 36 million of these things to create a contour plot. Okay, so graphically plotting these things is very computationally expensive and kind of defeats the point of these optimization algorithms. Okay, so when you run the optimization algorithm to find the minimum value or maximum value, you certainly don't want to be generally plotting them at the same time. Okay, I make you plot them so you get to see the lines, and it creates this nice visual of how the algorithms are working. But computationally, if you think about it, it's very expensive to do. Okay, so so we don't want to do a grid search in a multivariate setting. Okay, so so what can we do, right? And so there's a few different things, and I cover other methods in 102B, which some of you guys will take next quarter. But the one we're going to look at today is going to be coordinate descent. Okay. All right. And the way coordinate descent works is we turn our multivariate function into univariate functions, and then we apply a univariate optimization method. Okay. So okay. And the way we do this is we hold all but one variable constant. Okay, so we start off with some arbitrary values, and then we hold all the variables constant except for one. Okay, and we allow only one of the variables to vary, and then it becomes a univariate function. Okay, so we hold all but one variable constant. So so basically f of xy becomes f of x, and then we hold y equal to some y0 value, all right? And then we apply the univariate optimization. We apply univariate optimization method, and then so basically we find x1 and minimize f of x where y is held equal to y0, okay? And then we repeat for the other coordinates. Okay, so now that repeat for the other coordinates, basically using the updated value you just found. Okay, so then we optimize f of y where x is held equal to x1, okay, and we find y1 that minimizes this, okay, and so on and so forth. Okay, so to illustrate this, I've got an R script here, and I'll share this and I'll post this. I'll post this online. Sorry, I still have to do that with Monday's code. Okay. The code here is intentionally bad. Okay. You have to do coordinate descent as part of your homework, and I didn't want to give like away the full answer. Okay, but I have this, and it works. Okay. Don't do this for your homework. Okay. But this is just to illustrate how it works. Okay, I'm going to use this library called Plotly, which uses these OpenGL things. Okay, I'm also going to load up some code that I have for golden section search. Okay, here's the function that I want to optimize. Okay, it's x squared minus 2x minus 0.5 x times y plus 2.5 y squared. Okay, I can go over to Wolfram Alpha. And we can get a plot of this, so you can see, and basically, okay. Well, maybe that's basically we want to find the minimum of this, and it is at 40 over 39 and 4/39. Okay, this is the global minimum here. Okay. All right, so I'm doing this with Plotly. Plotly uses a lot of computational resources, so don't do this in your homework, okay? And so I create. What is going on? Okay, are you guys familiar with the function outer? Okay, so what? So here I have x. Okay. So x is this. X is a vector of length 71. Y is also a vector of length 71. Maybe I'll do 91. Okay, just to kind of get nicer looking numbers. Okay. Okay. So here's x. Basically increments at 0.05. Here's y. Oh, it's a little bit different. Okay. And outer creates a matrix. Okay, so here I've got 91, length 91x, length 91y. Outer is going to create a matrix, 91 by 91, and each coordinate is going to be basically the first coordinate, minus 1.5, minus 1.5, and it's going to plug it into the function g. G takes in two values here. My computer is going crazy. Okay, So if I look at what G is, or Z is, okay, this is a matrix 91 by 91, and it shows us the values when I plug in each of these things. Okay. All right, so I'm going to create a plot here, and I hope this works. Okay, so here we go. So here is our 3D. Can you guys see that? Okay, so this is what it looks like. Okay, and we want to find the minimum, which is going to be somewhere around here. Okay, but we don't know where this is. Okay, so I'm going to just start off at an arbitrary point, -1, +1.5. All right, and I will add this plot dot here. I hope. Okay, so each time I draw it takes a long time. Okay, and so I'm starting off at this location here. Okay, and so what I'm going to do is I'm going to hold one of my variables constant. Okay, and let's see. So here I'm going to hold y constant at 1.5. Okay, and so basically I'm going to plug in 1.5 here, and then and this becomes basically a function of just x, right? I've got x squared minus 2x minus 1.5 x times this plus 2.5. You know, I've replaced y with 1.5. Okay. All right. So now I have a function of just x. Okay, and basically this I'm going to add a trace of that line here. Okay, so you can just kind of see what this looks like. All right, so here is when you hold y equal to 1.5, you don't have a surface, you just have a single parabola. Okay, a single line, and it's this orange line right here. Okay, this is everywhere along this line is where y is equal to 1.5, and we can see the value of x. And so now I want to minimize this value of this orange parabola here. Okay, and so there's ways I can do it, right? I could just use plain old calculus, and I could say, all right, let's take the derivative of this thing, find where the derivative is equal to 0 to find where my x value is. Okay, so I could do that. But I'm just gonna just use the golden section search to do this for me. But I could do it myself manually. But so I'm gonna just say do use golden section search on this unidimensional function. Okay, and your search range starts at -1.5 up to 2. Tell me where do you find the minimum, and it says we find a minimum at 1.375. So if I go to right around here, you know, it's going to be right around 1.375. So I'll go ahead and I will plot that dot here. Okay, and so this purple dot represents the minimum of that orange line there. Okay, so from up top it looks like this, but this is that parabola there, right? Can you guys kind of visually see what's happening? So we lock in one value, all right? So it becomes a unidimensional function, and we're minimizing that one unidimensional function. Okay. Is there a way to turn off? Okay, so now it doesn't, that tooltip doesn't pop up anymore. Okay, all right, so now I've got x is 1.375, and I'm going to use that, and I'm going to just replace every x with 1.375, and so I have a function of just y. Okay, I have a function of just y, and we're going to find the minimum of this. Okay, so let me just show what the line looks like where I locked in x equal to 1.375. Okay, so here is this line at x equal to 1.375. That's you guys can barely see it. All right, can you guys see that? There's like a purple line here. Maybe I'll change the color. Color to, I guess I'll just do white. All right, so there's a line right there, and that represents what the function looks like when x is equal to 1.375. Okay, so it's right along there, and we're going to find where it's the minimum. Now, if I trace this down here, it's not exactly at the minimum. The minimum's a little bit off over here. So we're going to trace this down to kind of the bottom here. And so I've got a function of just x, where x is set equal to 1.375. It's a function of y, and we're going to minimize that. So I use a golden section search, and it tells me that the value of y that minimizes this is 0.1375. Okay, so we'll go ahead and we'll add a dot here. Okay, here, let me change this. Dark green is not going to show. Let's do yellow, I guess. Okay, so here's the minimum value right there, and then we would repeat this. So y is equal to 0.1375. I'm going to replace all of my y's with 0.1375. Okay, and let me see. I'll create this plot in yellow. Okay, and so there's the function there, and this will get us closer to the true minimum. Okay, so we don't get to just go diagonally from our starting location down to the bottom. We have to we just do one coordinate at a time. Okay, so this is why it's called coordinate descent. Is we turn our thing into univariate functions, and we do univariate optimization. So locking in y, we find the x that minimizes that function. Okay, and then once I find that x, I lock that in, and I find the y that minimizes this function. Okay, once I find the value of y that minimizes this function, I'm going to lock that in, and I'm going to find the value of x that minimizes this. Okay, and so I keep iterating. And then so my next iteration produces the next plot, or the next dot, which is we're getting there. We're getting pretty close. Okay, because we can see each step that we're taking, gets smaller and smaller, which is an indication that we're getting closer to the minimum. But this is how coordinate descent works. Okay, when you do this in your homework, most likely what you're going to see is you're going to see kind of a right. So you're going to have these contour plots or something. And probably what's going to happen is your plot will go straight in one direction, and then you'll go straight in the other direction, and then you'll go straight in this direction, and it'll probably be this kind of staircase pattern. Okay, so this is probably what you'll expect to see in your homework, depending on what you're doing. Okay, but this is kind of the signature effect of coordinate descent, is that you're doing one coordinate at a time, and so you get these straight lines. okay, perpendicular lines, because you've locked in this case, you've locked in x, and you find the y that minimizes, and then now we've locked in y, and we find the x that minimizes, and so on and so forth. Is that okay? What's happening here? So we started here, we went down, we went this way, this was the value that minimized, and then we traced this way, and this is the value that minimized, and then along this path, this is the value that minimizes, and if I continue it, I'm probably going to end up just slightly offset here, and so on and so forth. My graphic is getting a little bit buggy there. All right, is that good? Okay, we'll end there for today then. I'll share this code and you can mess around with it, and we'll see you guys on Friday.